This idea of yield is basically a way that we can measure how much product we actually produce when we perform or conduct a chemical reaction. So when we conduct a reaction, for example, this reaction here, where a substitution reaction, where we convert methane to chloromethane, if we actually conducted this reaction, perhaps let's say that we reacted 2 mole of methane with 2 mole of chlorine. Now theoretically, we should produce 2 mole of chloromethane and 2 mole of hydrochloric acid. However, in reality, if we do this reaction, we might only produce 1.5 mole of each. So this fact that theoretically we should produce 2 mole of each of these products if this reaction were to go to completion, however in reality we do this reaction and we only get 1.5 mole, is a demonstration of the idea of yield. So if we wanted to calculate the percentage yield, then we would say that we only collected 1.5 mole of each of our products. So that is our actual amount of product. And our theoretical amount of product, so our theoretical amount of product assumes that the reaction can go to completion. And so our theoretical amount of product is 2 mole. So in this case, if we reacted 2 mole of methane with 2 mole of chlorine to produce 1.5 mole of each of these products, then our percentage yield would be 1.5 over 2, or 0.75. And so we'll usually multiply this by 100 to get it into a percentage. So what we really have is 75% yield. So we can say that if when we performed this reaction, we managed to get a 75% yield. We produced 75% of what we could have possibly produced. If we did everything perfectly and we were somehow able to ensure that this reaction occurred to absolute completion, we used up all of our reactants, then theoretically we could get 2 mole of each of our products. However, in reality, with the resources available to us, we could only get 1.5 mole, so our yield is 75%. So that is simply all that yield is. It's a measure of how much product we can glean from a reaction, whether or not we can get all of our reactants to react to completion or not. Now, if we have, rather than just calculating a yield for a single reaction, we often have to calculate the yield for a series of reactions. So if we have methane, as before, and then we produced from that our chloromethane, and then from there we produced methanol. Now, we just calculated that the yield of this reaction was 75%. And we'll say that we conducted this reaction as well. We produced methanol from chloromethane. And we'll say that this had a yield of 70%. Now, if we want to calculate the yield of this whole process, we can do that quite easily. So we know that producing chloromethane from methane, we're only going to get 75% of the possible reactants. Only 75% of our methane will actually be converted to chloromethane. And then of that chloromethane, of that 75% of that 75% of the methane that reacted and that has now been converted to chloromethane, only 70% of that will then be converted to methanol. So if we wanted to calculate the percentage yield for the entire process, that would be equal to 0.75 times 0.7. So what that gives us is 0.53. So if we have one step with a yield of 75% and the next step with a yield of 70%, then our net yield for the entire process, because we've lost some, we sort of haven't produced each step to perfection or to completion. We haven't managed to react all of our reactants in either of these steps, and so both of these steps have meant that we've lost some of the products that were possible. So our net yield is only 53%. Only 53% of the methane that we started with ends up as methanol. So now if we look down here at a bit of an example, we've started with ethene, we've reacted it with water with a solid phosphoric acid catalyst to produce ethanol. From there, we've reacted the ethanol with oxygen to produce ethanoic acid. So these are standard chemical reactions, chemical processes. Now, we've started with 100.8 grams of ethene. We've ended up with 96.0 grams of ethanoic acid. And we know that the yield for this step is 77%. Now, what we're going to try and do here, is figure out the yield of this step here. We want to know this yield. So we'll call that yield X. So, first of all, we want to find the yield of the entire process. So we want to find how much of our ethene is converted to ethanoic acid. Well, the best way for us to do that is to figure out the mole of each. We know that 1 mole of ethene will produce 1 mole of ethanol, and that 1 mole of ethanol will produce 1 mole of ethanoic acid. So we've got a 1-to-1 ratio throughout this whole process. So if we wanted to work out our mole of ethene, we've got 100.8 over 28, which gives us 3.6 grams. If we look over here at our mole of ethanoic acid, then what we have, this should not say grams, obviously we're looking at mole here. So here we've got 96.0 grams over 60, which is the molar mass of ethanoic acid. So we get 1.6 mole. Now our percentage yield is therefore going to be equal, because we're starting with 3.6 mole of ethene and there's a 1-to-1 ratio. Theoretically, we should end up with 3.6 mole of ethanoic acid, but we only have 1.6. So the yield for the entire process is 1.6 over 3.6 times 100, because we're looking at a percentage. That's equal to 44%. So now we have a yield for the whole process of 44%. We want to find a yield for this step here. So if we just make a bit of room up here, then if we know that the yield for the whole process is 44%, and that is equal to the yield for the first step multiplied by the yield of the second step. So what that means is that we can create an equation like this. So 0.44 is equal to 0.77 times X. So X here is not the percentage yield, but just the decimal value. And so that means that our yield for that second step, just some simple algebra, is equal to 0.44 over 0.77, or 58%. So the yield for our second step is 58%. So here we've used the masses combined with the molar masses of our initial reactant and our end product to figure out the yield of the entire process. And because we know the relationship between the yield of the entire process and the yield of each of the steps, we were able to use this information here to work out the yield of our second step. So that's just one example of a possible calculation that involves yield. And so there's obviously lots of different ways or lots of different situations where we may need to use these relationships and our understanding of the actual amount of product over the theoretical amount of product in order to calculate some figures such as this.